The second method that we use to solve boundary value problems is called the finite difference method. And you should probably recognize that finite difference has a lot of callbacks to our previous approximating derivatives with a finite difference because we didn't want to do the hard calculus of trying to remember all of those different ways of figuring out derivatives of different equations. And so, very similarly, we use finite difference approximations for the derivatives to convert an ordinary differential equation into an algebraic equation. So again, we've got this ordinary differential equation. It's a second order, and we want to try to convert this into an algebraic expression. Okay, and we're going to use this term right here, but I'm going to take a little bit of time to just kind of derive it, because ultimately we want to take away all these little d's and challenging parts and hopefully replace it with something a little bit easier right here. Okay, so let's remind ourselves what dt dx is if we're using, say, the forward difference approximation. Well, we would do ti plus 1 minus ti, and then we would divide it by, well, rise over run. In this particular case, it's going to be xi plus 1 minus xi. Or it's going to be ti plus 1 minus ti over delta x, assuming that the spacing in between two x's are equal, the step size. Now what about a t d2 or d squared t over dx squared? Okay, so this term right here is what we're talking about. Well, this is nothing more than d dx of, well, this thing right here, dt dx, which is nothing more than d dx t prime. So if that's the case, then we can come over here and we just say, well, this is going to be t prime I plus 1 minus t prime I all over, well, same thing, delta x, or xi plus 1. So you should be able to see the difference, or rather the very few differences, between this one right here and this one right here. Except now we got to spend some time and replace this first term right here and the second term with, not surprisingly, stuff from up here in the top row. So now I'm going to make another one, d2 t over dx squared equals this first one right here, okay, is this guy, but I have to increment the I by 1, so I'm going to make this be t I plus 2 minus t I plus 1 divided by delta x minus this sign right here. This one is just the same, ti plus 1 minus ti all over delta x. And then I need this one right here, all over delta x. All right, so now we can hopefully see kind of where this delta x squared comes from. Okay, so let's just take a little bit more time and talk about, well, converting this into this format right here. So I'll do a ti plus 2 minus, well, there's two of those, ti plus 1. And there is a positive, two negatives make a positive, ti right here, all over delta x squared. All right, so now we're getting very close to the format right here in the bottom left. The last thing we need to talk about is, why is it I plus 2, I plus 1, and I, instead of over here, I plus 1, I, and I minus 1? Well, it's fine because we can come in here and it's the same equation if we just add 3 to every one of these terms, or subtract 4 from every one of these terms, or what have you. These i's are actually arbitrary. All we're really talking about is that we're going 1 back in time from this one and 1 forward in time from this one. So if I arbitrarily subtract 1 from each one of these subscripts, minus 1, minus 1, minus 1, I'm then left with ti plus 1 minus 2 ti plus ti minus 1 divided by delta x squared, which means then that this formula right here is nothing more than the finite difference approximation of not just the first derivative, but of a second derivative, which is essential for second order finite difference expressions in ordinary differential equations. where's my mouse? There it is. Okay, so effectively, we're going to use that finite difference approximation for the second derivative and plug it into our differential equation, which is going to give us then this algebraic expression, okay? And we're going to have then these txi's, this function that we really care about, broken up into various ti's, okay? So again, we take this second order ordinary differential equation, we're going to convert it into this algebraic expression, and now we can write this expression for each one of those xi's, okay, making a system of linear equations. So that when it's solved, it's going to give us the approximate solution. Okay, we're after, of course, t for all different values of x, and so if we can solve the system of linear equations, we're going to be left with just that. All right, so just to recap the problem, we've got this ordinary differential equation, we've got some constant terms inside, okay, namely h and Ta as before with the temperature rod. And then we've got, well, two values. These are both boundary conditions. Boundary condition 1, boundary condition 2. But in this case, we're going to try to combine them into an equation set. So we're going to discretize, okay, using what we had before, using this first term for the second derivative inside the ODE. We're going to replace h with 0.01, we're going to replace Ta with 20, and now we have this equation which is satisfied for a whole bunch of different i's. Okay, so there's lots of i's right here. When I is equal to 1, when I is equal to 2, when I is equal to 3, so on and so forth. Okay, but before we do, let's try to make it a little bit easier so we can see this equation. So what I'm going to do is I'm going to multiply delta x, okay, across all these different terms, and I'm going to try to isolate ti. So I have now ti plus 1 minus 2 ti plus ti minus 1 plus delta x squared times 0.2, okay, minus 0.01 times delta x squared times ti equals 0. Okay, and we can notice then that I've got a ti term right here and a ti term right here. So I'm going to do one more equation, ti plus 1 minus 2, okay, plus 0.01 delta x squared ti, okay, plus ti minus 1. I'm going to bring this all over to the right hand side, which equals minus 0.2 times delta x squared. Okay, and so this equation at the very bottom is the one I'm going to use, okay, in my future applications of applying an I at each one of these three different terms. All right, well, we can see this equation that we've just had before. Okay, we can see the right hand side as we calculated, and then right here I'm going to make an assumption and call this C right here. Okay, it's a value that's not going to change at all, right? And of course it's going to be 2 plus 0.01 delta x squared, and if delta x is equal to 2 right here, well, this is going to be 2 plus 0.04 or 2.04. Okay, so now I've got this equation, and now I'm going to plug in I equals 0. Well, when I is equal to 0, it's actually right here. Okay, it's when x0 is equal to 0, and that's actually known. But that's a simple trivial equation. I don't even need to use it right here. So I get this first equation for free. Effectively, this first equation is that t0 equals 40. Yes, there's a whole bunch of other unknowns, but essentially this first equation, the first row, okay, in this matrix vector problem, is trivial. Yes, I could treat it as an unknown, but I actually use this one equation to satisfy that unknown. Now, if delta x is equal to 2, and I want to go from 0 to 10, okay, such that right here x is equal to 0, right here x equals 2, x equals 4, 6, 8, x equals 10, okay, I now need to take my 0, my 1, my 2, 3, 4, 5, and I need to know, of course, what the t value is at all of these unknowns in between my boundary conditions. So I've got a column right here of unknowns. Okay, I'll just call this my generic sort of t vector because I want to know what my temperature is at all different values of I. or more specifically, at different values of x. All right, so we talked about that first equation. What about the last one? Well, T5, okay, is equal to 200, okay? T5, when x equals to 5, is also a boundary condition. This is a little equation. Yes, it doesn't look like much, but it is still an equation, and a very trivial equation, so therefore I have the first and the last rows, which are quite trivial. What's most exciting is the ones in the middle, T1, T2, T3, T4. Let's start by plugging in I is equal to 1. Well, if I is equal to 1 right here, this whole subscript becomes T0. It just so happens that I have T0 right here, and it's known. Okay? If I is equal to 1, this one becomes a 1. Okay? And if I is equal to 1, this one becomes a 2. Which means then that I have an equation right here as a function of T0, T1, and T2, and a whole bunch of constant terms. If I write that in matrix notation, I get the coefficient right here in front of T0. Okay, there's a 1 right here. I get minus c, the coefficient in front of T1. Okay, that's this right here. And I also have T2. Okay, the coefficient right in front of T2. All right, so I've got 1, I got minus c, I have 1. Okay, times T1, T2, and T3 respectively. And then on the right-hand side, well, I can plug it into this spot right here, minus 0.2 delta x squared. Then I increment I from 1 to 2. And then I go back here and I replace this one and make it T1. I make this one to be T2, and I make this one to be T3. And I'm going to be left with 3 values, 1 minus C, 1, okay, coming up with the third equation necessary to satisfy the third row. I do the same thing with I is equal to 3, and as I is equal to 4, and all I'm doing is I'm incrementing this subscript, and this subscript with the exact same equation necessary to solve for these unknowns inside this matrix 1 minus C1. So you can kind of see this pattern that once you've solved one of the equations, it's really easy to just go through and replace all the other terms inside this matrix as you go down diagonally. All right, so now I'm left with this matrix right here, and we of course call this our A matrix, our coefficient matrix. We call this, well, our unknown vector. We can call it T for now because we're after T, we're not after X. And we can call this our B-side vector. And so now we've got a system of equations, and we can use direct solvers. And so we've seen LU decomposition, we've seen Gauss elimination. There's some other solvers out there. One is called the tridiagonal solver, or Thomas's algorithm. This is not covered in 273. And we have iterative methods as well, Jacobi methods, Gauss-Seidel methods, and these also are not covered in 273. But if you're really enjoying this stuff, you should take a look at some of these and learn a little bit more about them. Okay, so just as a sum up, we have this ordinary differential equation right here. We've got 2 boundary conditions at the beginning and the end of our domain. And instead of converting it into 2 first-order ordinary differential equations, we're going to convert it into an algebraic expression right here. Okay, we're going to set up the various points in the equations for each one of these discrete points, and so we can rework this equation into a little bit easier to compute, this equation right here. And then we kind of step through having I is equal to 1, I is equal to 2, I is equal to so on and so forth, and slowly fill in this equation. Okay, and then it just takes a little bit of effort to solve for this matrix vector right-hand side system of equations. All right, so we're going to do this example after I go back up and do this example in MATLAB. And hopefully the example will help clarify some of the theory that we had talked about. All right, well, I'm in MATLAB again, and you can see that I've saved a script called Finite Different Examples, W Winter 2020, and I'm going to go back to my T-shoot and copy out a couple of the important things that I need, in particular this column, or rather this set of data right here. And I'm also going to label this finite difference method for boundary value problems. Okay, and in particular, this is for the temperature rod problem. All right, and so we have these same constants from before, so I'm just going to skip that. If you know how to do that and you're okay with where those come from, if you've seen the previous couple of parts for these lectures. And, you know, I've got the exact same values for my left temperature and my right temperature of 200. All right, well, if you recall then, we need to kind of convert this second order ordinary differential equation into, well, an algebraic expression right here, and then we had to set up the sort of equation for all these different discrete points. Okay, so we're going to go off and we need to maybe have some variables, especially for this one, and I called it C. So I'm going to come in here and define C. Okay, and so C is nothing more than minus, okay, 2 plus HC. Okay, HC is 0.01. Okay, that's what this value is right here. Times, well, delta x dx. Square that, or not square that, square that. Okay. And these are going to be, I don't know, these are form other constants. So I've got C right here, and let's take a look at what else I have. I also have this, which is going to be constant for a lot of my b-side vector. Okay, so I'm just going to call that actually a little b right here. Just remind me that's on the b-side vector. And I've got 0.2 times, well, dx squared again. Okay, so now I've got a term for this coefficient in front of ti, and I've got a term for the b-side vector, and then I've got a whole bunch of, well, coefficients that are just ones for the other ones. Okay, so now I need to kind of set up an empty matrix. Okay, so I'm going to come in here and just say set up an empty matrix A. Okay, for the system of systems, or rather the system of equations. All right, well, it makes sense to call it A, right? And I'm going to have it zeros, okay? And in fact, I can have it, well, size n. And if I want to take a look at that, I can always come back and do help zeros in the command window. All right, so if you recall, we looked at this before, and we had used this one, and now we're going to use an n by n matrix of zeros, where we just define n. All right, well, if we have n, we need to maybe discuss how we're going to set up n. So before n, we need to, well, say n is going to be the length of some sort of vector. Well, what vector is it? Well, it's going to be the vector of the domain, okay? These temperatures right here. Okay, and if we recall, all right, we had one unknown right here, 2, 3, 4, 5, 6 right here, okay? That's, of course, with a delta x of 2, so in the meantime, maybe I'll set this to be 2. Okay, and so we need to kind of make our x vector. So we'll make our x vector like we did before. X is going to equal, well, the left-hand side, which is x equals 0, a dx, all the way up to 10, just like we had before. And then we're going to take the length of x and define that to be our size of n. Maybe I'll just make a little comment right here, form x vector. All right, so now we've got our n size, and of course, if dx is equal to 2 right here, then we know, okay, that we're going to have 6 elements inside of the x vector, which means we're going to have n is equal to 6, which means we're going to have a 6 by 6 empty matrix right here, a whole bunch of zeros. Okay, and in fact, we can come in here and define these. Right, there's our x, here's our length, and then here's our a matrix right here, which is all zeros, ready to go. To be replaced with all these ones and these minus c's. All right, I'm going to set up my b-side vector. Okay, I'm going to do it capital B, and it's going to be very similar in the sense that it's going to have 1, 2, 3, 4, 5, 6. So it's going to also be zeros, but it's not going to be a matrix, it's going to be a column vector. Okay, so we're going to have it n by 1. Remember, the first element is going to be, or rather the first argument in the zeros function is going to be the number of rows, and this is going to be the number of columns. All right, we will suppress those. But if you want to check it, hover over it, hit F9, or copy it down into your command window. All right, so of course we're going to replace these zeros with all these terms right here. Let's go back to this one right here. All right, well, there's a couple of special entries inside of this A matrix. In particular, the first row and first column is a 1. So we're going to come in here and say 1, 1 is equal to, well, it's equal to a 1. Okay, and there's also a special entry at the very bottom right down here. We also know then that the 6th row and the 6th column is also equal to a 1. And we have the same sort of thing with B's, except B's are a little different. Okay, we know then that there is only one argument in the B side vector. I'm doing a capital B right here. We have the first element, which is not a 1, but it's going to be 40. Okay, and 40 is going to be the right hand side, so I'm going to take this and pop it down here. Okay, so it's going to be TL, the temperature on the far left. And this one right here is going to be temperature on the far right. Okay, so what we've done here is that we've defined 4 numbers inside this A matrix, here, here, and B matrix, or rather B side vector right here and right here. Alright, so these are, I don't know, known quantities. Okay, and now we need to go through and we need to start, first of all, on this second row right here. Alright, well, let's take a look at it. Well, we need to place, okay, a C, okay, at the second row and second column. So I'm going to come in here and do 2, 2, okay, and make that into a C. And you might say, well, why is it not negative C? Well, that negative sign in front of that parentheses was already encapsulated right here. So I can take that away if I wanted to, but I'm going to leave it because effectively I'm just going to replace that second row, second column with the value of C. If I wanted to, I could take this negative sign away right here and put it right here. Okay, and since I did that already, I guess I'll just leave it right there. All right, that takes care of the negative C's, at least in this spot right here. And then I need to do one before it and one after it. Okay, so I need to go one before, not in row, but in column, and one after it. Not after it right there. Okay, both of these are ones. Okay, and so once I do this, right, I can repeat it multiple times. So I can, of course, come in here and I can change this to be, well, 3, 3. And this, of course, is the third row, but one before it is 2, and one after it is 4. All right, well, I got to do this, 3 more times, and so this is a perfect time to do a little for loop. So for loop, okay, I'm going to increment from I. I'm going to start with it at 2, the second row. I'm going to go all the way to n minus 1. Okay, I don't need to go to the 6th row. The 6th row is already defined. I do need to go, though, to the 5th row. So I need to go all the way to the, well, I is equal to 5. All right, well, let's put a little end right here. Okay, and then let's talk about these 3 different ways of replacing different values inside my A matrix. Well, the first one then is going to be this A, well, I. Okay, and that's, of course, this minus C right here. So let me suppress that one. Let's delete that for the time being. Okay, and then I've got another one. Okay, I've got one in front of it. Okay, so I'll need to make a little copy, and I need to go 1 in front of it, or behind it, and make that into a 1. And then I need to go 1 after it, so plus 1, and make that a 1 as well. Okay, I'm going to suppress all those things right here. So now I've got a for loop that's going to step through the 2nd to the 5th row, and it's going to make all the diagonals minus C, and it's going to make 1 in front of the diagonal and 1 behind the diagonal, different ones. Okay. All right, well, let's do this, and we'll see how it turns out. So let me just do this and hit F9. Okay. Oh, undefined function C, so let me come up here and define C. I'll run these right here. I'll run this, hitting F9, and then I'll select my for loop. Okay, and now I'm left with this matrix, and it's kind of hard to see, so what I'm going to do, format short, and hit A again. All right, and now I can kind of take a look at my A matrix right here. Sure enough, I've got 1 in the first column and in the first row. I've got 1 in the last column and last row, and I've got this 1 minus C1 sort of pattern the whole time. Okay, let's take a look at what my C value is. My C is 2.04. That makes sense because I've got 2 plus 0.4 right here. Once I take my delta squared, which is 2 squared, which is 4. Okay, so that all looks good. And now I need to talk about my b side vector. Well, my b is 40, 0, 0, 0, 200 right now. Okay, which means I'm missing all this content because I'm expecting some sort of negative values right here. Well, that's fine. I just need to work on that inside my for loop. I'm going to go from the second to the second last row. So b, okay, it's always going to be the first column. So I just need to step from, well, I, okay, equals, well, little b. So I'll rerun this here again. I'll hit F9, and I'll take a look at, oh, undefined functional variable b. Let me go up and run it. It's line 13, hit F9, come back down here, run my for loop, and now I've got my b vector, and it's 40, minus 0.8, minus 0.8, minus 0.8, minus 0.8, 200. Okay? So there's 6 unknowns, but 2 of the unknowns are trivial, so I really only have 4, but I'm still going to use a 6 by 6 matrix, and then, of course, a 6 by 1 b-side vector. Alright, well, inside my script, I think it was really helpful for us to kind of see A and B. Okay, so I'm going to put some of these little semicolons so I can suppress the output right there, and just take a look at what A is and B is after I run this entire script. Alright, so I've done a bunch of work, so maybe it's probably about time for me to run it and see if it works. Sure enough, it does. I get A and I get B. Okay, maybe I need to clear my command window at the very beginning of it and clear all and close all my variables and my figures. Okay, things look a little bit better now and a little bit cleaner. Okay, I don't necessarily care about looking at B right then, so maybe I'm going to come in here and suppress little b, little c, my x vector, my n, okay, and all these quantities right here. Alright, I've got A and B, okay, and so MATLAB, of course, can implement a whole bunch of different techniques to solve a system of equations. And I'm going to use the inverse of A and multiply both sides by that. Okay, so effectively this vector right here, I'm going to call it the t vector. Okay, it's an unknown vector. Of course it could be x, but since x is already defined as my x vector, this is my unknown vector. Okay, and I'm going to multiply both sides by the inverse of A, which means I'm going to isolate that unknown vector t. Okay, and if I inverse A and multiply it by B, on the left side multiplication, of course, according to the rules of matrix math, then I'm going to get t. So let's run this. And there you go. I've got some sort of vector that goes from 40 degrees up to 200 degrees, and I've got maybe my profile here in between it. All right. Well, if I've got that profile, I might as well take a look at it. So I'm going to do a figure. I'm going to plot. I'm going to plot x versus t. Okay, let's take a look at it. All right. Well, I've got a couple of data points, okay, that are going to link this from 40 to 200. So let me add some labels here quick. Okay, and I want to take a look at these individual points, so I'm going to do a line, and I'm also going to do circles. I'll make red circles right here, and I will do a blue dashed line right there. Alright, I'll hit run. It's running. Current plot held. Alright, and so now we can see that I've got 1, 2, 3, 4, 5, 6, okay, unknown values, okay, where the first and the last were my boundary conditions, so those are known. So I'm really only solving 4 of them, although I did have to do a matrix inverse problem with a 6 by 6 matrix. Yes, technically you could change this down to a 4 by 4, but I find that making it to be the full size is a little bit more clear and helps out understand that the boundary conditions of the first row and the boundary conditions of the last row are helpful to see inside this matrix format. Okay, well, all of these are straight lines in between them, and so if I wanted to increase the resolution, I could do, well, as expected in this class, I can decrease the size of delta x. Before I do, I'm going to change it into a delta x of not just 2, but of 5. So I come over here, I'll change my dx to be 5. Let it run again. Plot is right here. Okay, and you can see then that there's a value of 40 at the initial boundary condition. There's a value of 200 at the other boundary condition. And then I have one unknown effectively, even though it was a 3 by 3 matrix that I was solving for. The first and the last equations were trivial. I've got now kind of a profile of t for all values of x that I've asked about. Okay. So this is the fewest number of unknown equations for a boundary value problem. Of course, you can go one less than this and just assume that there's some sort of straight line in between those boundary conditions. And in some cases, that sort of zeroth order model, if you will, is an approximation. But of course, if you have some other information, it won't be sufficient at modeling the dynamics and the changes of this particular ordinary differential equation. So let's go back in now and let's start changing our size, our step size, to now be 1, so that we have 11 points. Okay. Here's our values going from 40 to 200. Okay. And we've got these different points. And each one of these little segments is straight, of course, but it's starting to look a little bit better in terms of some curvature. Let's go to 0.1. Okay, and now we're starting to lose the ability to distinguish all the different circles independently from each other because there's some overlap. And essentially, though, we've got a pretty smooth profile, or rather function or solution, the value of t for all values of x that we care about.